Welcome to Homework Lib.
Hi, so over here we have the reaction of the composition of a certain compound that is 𝑋𝑌2 as a gas that is going to be in equilibrium with its decomposition products, that is X gas plus 2 moles of Y as a gas. So remember that whenever we have the values for Kp, Kc, and Ky, what we need to get is the change of the amount of moles that we have as gases. So in this case, the change of mole of the amount of gases is going to be equal to, we have as the products, we have 3 minus 1. So the change of amount of mole is equal to 2. Recall that Kc and Kp are related as follows. The value for Kc is equal to 1 over RT to the change of amount of mole multiplied by Kp. And similarly, Kp is going to be related to Ky by the total pressure of the system that we have at equilibrium, multiplied by the same value of delta N. So for this problem, we're told that we start employing a 13.8 liter vessel, which contains 0.25 mole of 𝑋𝑌2. This is going to start to decompose, and we are only given the pressure that we achieve at equilibrium. So whenever we reach equilibrium, we have a total pressure of 840 millimeters of mercury. I'm going to transform this quantity into atmospheres, since it is going to be easier to do the calculations relating that to the gas constant. So the value of 840 millimeters of mercury is equal to 1.105 atmospheres. So for the reaction of decomposition, what we're going to get is that if we look at the reaction table, the degree of dissociation is going to tell us what amount we're going to get at equilibrium. So initially we start with an amount N0 of moles of 𝑋𝑌2, 0 of the decomposition products. A portion that we're going to call alpha is going to react. We're going to generate alpha plus 2 alpha, and the amount of moles that we're going to get at equilibrium is N0 minus alpha, alpha, and 2 alpha. We know that the total pressure of the system is going to be equal to the pressure of X plus the pressure of Y plus the pressure of 𝑋𝑌2. And according to ideal gas law, remember that pressure is equal to nRT divided by volume. The volume is going to stay the same for all of the calculations that we're going to make, as well as the temperature. So we can factorize it out of all of the values that we have here. So we're going to get RT divided by V multiplied by amount of mole of X plus amount of mole of Y plus amount of mole of 𝑋𝑌2. This is going to allow us to generate an equation with the degree of dissociation, which is going to be RT divided by V multiplied by initial amount of mole that we had minus alpha, this is the amount of mole of 𝑋𝑌2, plus alpha plus 2 alpha. So minus alpha and alpha cancel out, and we get that the total pressure is going to be equal to RT divided by V times N0 plus 2 alpha. We can solve directly for the value of alpha, and we get that volume times total pressure divided by RT is going to be equal to N0 minus 2 plus 2 alpha. Thus, alpha will be equal to volume times Pt divided by RT minus N0, and all of this divided by 2. Let's replace the values that are given to us. The value for volume that we have is equal to 13.8 liters. The total pressure on our system is going to be 1.105 atmospheres. Since we have liters and atmospheres, we need to employ our gas constant in the appropriate units, that is 0.082 liter atmospheres over mole Kelvin. And here we need to multiply by the temperature that is 300 Kelvin. Notice that the value that we're going to find here is going to be in units of mole. Now, minus the initial mole that we have on our system, that is 0.25 mole. And finally, we're going to divide by 2. The value alpha, that is the amount of moles that are going to be consumed, is going to be equal to 0.185 mole. Remember that this is not entirely the degree of dissociation. This is just the amount of mole that is going to be consumed. So to know the percent decomposed or dissociated, we're going to get 0.185, that is the portion that was consumed, divided by 0.25 times 100. And the result is 74%. So 74% of the compound is going to be decomposed. So now we can get the different equilibrium constants for this reaction, employing the values that we got. So for example, for Kc, what we know is that this is going to be equal to concentration of Y squared times concentration of X divided by concentration of 𝑋𝑌2. Recall that from Y, we're going to generate in amounts of mole 2 alpha divided by my volume. This is going to be squared multiplied by alpha divided by volume divided by N0 minus alpha divided by volume. This is in terms of concentrations. So replacing the values for alpha, the value that we find for Kc is going to be equal to 2.046 times 10 to the minus 3. Remember that we don't put units on the equilibrium constant because we're always relating to a standard state in the case of concentrations of 1 molar, in the case of pressures of 1 atmospheres, and in the case of fractions to the fraction of 1, the unitary fraction. So this is the value that we get for Kc. So now with this we can return to our relationships, and we know that Kc, as we stated, it was 2.046 times 10 to the minus 3. We can proceed with the calculation of the other two quantities employing this part over here. We know that Kp will be equal to Kc times RT to the delta n. We said that the value for delta n in this case was going to be equal to 2. So we get the value of RT. We're going to employ liter atmosphere since we are using that as reference for all of the cases that we had. So 0.082 liter atmospheres over mole Kelvin. The value in Kelvin is going to be equal to 300. Actually, let me put it down here because we're not going to have enough space. So Kp would be equal to 2.046 times 10 to the minus 3. This is the value for Kc, times RT, 0.082 liter atmospheres over mole Kelvin. Notice that over here we have the definition of molarity, times 300 Kelvin squared. So Kp will be equal to 1.238. Now we can proceed to the calculation of Ky. Kp and Ky are related, as this equation states. So the value for Ky is going to be equal to Kp divided by the total pressure multiplied by the change of n. So this is going to be 1.238. We said that the total pressure was 105 atmospheres. And this is going to be squared. And the result for Ky thus is equal to 1.014. And these are the three values that we need to take as the end of the problem. Ky, Kp, and Kc. There we go. So with that, it would be all. Thank you very much and have a good one.